your de Broglie wavelength, that's telling you how fast, the distance you're vibrating. If you're only vibrating a Planck distance, or Planck, 10 to the minus 34, meters, that's nothing. No one's going to see that. It's not going to affect anything. It's not going to do anything. Okay. But when they show this with it, the baseball, where's the vibration? If this was an electron, it would be vibrating. But yeah, they don't. You can't compare a baseball to something that vibrates as it moves. That's stupid. And they all know that the electron vibrates and particles. They know it, man. So why do they keep saying this represents an electron, and that's why an electron isn't a particle? Because no. It doesn't. This is not, unless you got a motor in there that's going to make that baseball oscillate like an electron. It is not comparable to an electron. It has nothing to do with that, man. Okay, if you wanted to do this experiment on a macro, a baseball type thing, right? Macro level, right? This is your baseball, right? Or it's tennis ball or whatever, right? You would need to put a motor inside there. Say a tennis ball, so it's hollow. Put a motor in there so that it vibrates this middle, this way and this way. This would be the vibration of the ball. Okay? And on top of that, right, you would have to spin it. So electrons spin. Also, light spins. Photons spin. Okay? So you need this to be spinning, for one thing. And you would need it to be oscillating, right? Now, this wouldn't be oscillating this way because light oscillates in the direction it moves, right? So the baseball would be ball representing the electron or whatever. This is right here, right? This is your big slit, right? Okay. This ball, okay, is going to have to be spinning this way on it because it's moving this way. That axis it moves on, right? It's spinning around it, right? For one. Number two, okay, as it's moving this way, it has to be vibrating. Okay, you shoot it out of your gun, right? This camera's the gun. It comes out, and it's doing this. Boom. Then, okay, if you did all that, okay, I guarantee you would get this type of interference pattern, right, from this baseball. No doubt. Because that's how statistics and probability works, right? Now, this slit, right, has to be 25 times, the distance between this slit and the other slit has to be 25 times the distance from here to here, right? This width right here. So, obviously, you couldn't just have one gun with a baseball shooting out, right? They would never, you couldn't get them so that they would go into both slits or whatever, you know what I mean? But, just like a laser, remember up here, right? How big the laser has to be giant, compared to these little tiny whatevers. It's going to encompass at least part of each one of those slits, right? So you would need it like down here. You'd have to have like a whole bunch of barrels, with tennis balls in it, right? That you shoot out at the same, keep shooting, more, shoot them, then shoot some more, just like a baseball thing. When you go to the baseball batting cages, right? But you'd have a whole bunch of them shooting stuff out. So all of them oscillating as they go and spinning, right, rotating, right? And then that way it would be like up here, the batting cage would just you'd have all tennis balls all thrown around here, right? If you did that, guaranteed, you would have a diffraction thing just like down here, just like this, just like a interference pattern that you would get on a quantum scale. Okay, like I said, we did our slits. We know our width needs to be, whatever light we're testing or whatever. The slit width has to be at least even or smaller than the wavelength of the light, right? Or electron, whatever. It's got to be as small or smaller, right? What about the width? The separation between the two slits, right? We already went over that too, you know what I mean? The different, but it's about 25 times in this example. This is 25 times the width than a single slit, okay? So all we have left is the laser pointer, say the two double slits, right? and your wall or whatever you're going to display it on, right? What's the distance between these? You know, what's the deal with that? I can't be exact and tell you stuff. I have only done this once, and it was like 30 years ago, and I just did it with a cardboard box in the sunlight. You know what I mean? I can't remember what the hell, you know. It was just a little thing, though, you know what I mean? But I think that, you know, if you use a laser, right, you want it to have a lot of distance between the two slits in the wall, okay? At least that's what I see on YouTube, you know what I mean? The laser seems like it's maybe half the distance as it is from the wall, you know what I mean? You have at least a little bit of distance, maybe a couple feet or something, you know what I mean? But there is one thing that you need to really, really know, is this right here. You got the double slits here. I drew them again just so you can see. If the red came out of the left side, right, this blue line, right, this blue V, that was from the right slit, right? You have to be far enough away from the wall for these two. See how I got the V's, right? See how they overlap right there? You have to be far enough away from the wall to at least do that. You know what I mean? And most likely you got to be even further. All right. But, you know, this next stuff here, what I'm going to talk about right here, you know, don't quote me on everything on this because I just got it off of Google. You know what I mean? Like I said, I'm going to buy a bunch of stuff to do this, right? So I got these crystals here, these prisms or whatever, 3-part beam splitter, all these glass prisms, some mirrors and stuff like that. And I got this, I got the stands, 5 different experimental things. You know, they got 1 slit, 2 slits, 3 slits, 4 slits. I think you go up to 4 slits, maybe even 5. All kinds of different trellises, combinations. The slit sizes are all different. You got single and double, and round holes, whole bunch of different stuff there. You can see here there's 1, 2 slits, 3 slits, 4 slits, and this was only like $4, so I got it. It's a linear diffraction grating, and then I got another one because it's only $4, and it has also the 13,500 lines per inch. Jeez. And I got some polarizing film. I got 3 pieces, so I'm gonna. Cause they're idiots. I swear to God. I'm looking at this polarized, you know, paradox, you know, where you put 3 of them together and you know they're supposed to cancel. You put 2 together and it cancels out all the light. But if you put a 3rd filter in, you know, now all of a sudden you have light. It's like, it's not. It's like, what is? These people are like retarded. I swear to God. And I got a bunch of magnets. I got like 1,000 assorted magnets between all the different ones I did. Plus I got these bar magnets, and I got these cube magnets. You can see how tiny they are, though. I have over 1,000 magnets once these come in. When I say that, like, and these are all about going smaller, right? Like if you have smaller width of the slits, right? You get bigger lines, right? Because you got lines like this, right? Look at that, going across. That's your diffraction pattern, or whatever you want to call it, interference pattern. So you would think smaller width, you know, you would get smaller lines, right? Smaller whatever. No, you get bigger lines, right? But only in the X direction, only in the X axis, okay? Not going up and down or whatever, right? But if the height, right? If you make the height smaller, right? Again, it does the opposite. It makes the fringe vertical, you know, the height of these lines, it makes them taller. You know what I mean? If you make the slit shorter, it does the opposite. You know what I mean? But when you're doing this stuff, right? Like when you make the smaller width, you're getting a sharper image. You're getting a bigger lines, but you're also getting a dimmer light. You know what I mean? Smaller the hole, less light you're going to get, right? It's going to be dimmer. Same with the height, okay? You don't want it to be too big. You definitely don't want it to be small. You want it to be definitely like a rectangle, you know what I mean? The height can be as high as forever, you know what I mean? They say infinity, you know what I mean? So it can never be too high, okay? But it can definitely be too short, okay? And if you have it too short, you know, you're going to have a crappy picture, man. It's going to be all blurred together, you know what I mean? So what about separating the, you know, what's the distance here? What if you make this distance smaller in between your slits, right? More fringe spacing, right? See these things? They space out more. They get longer. If you separate them more, right, instead of making it smaller distance, right? And the reason why I'm iffy about these, what I'm saying here, this part here, right, is because all these things here, right, with the wall, the laser on the wall, the height of the, well, not the height as much, but the separation of the slits, the width of the slits, right, all them things, right, they make make the thing focused or make it unfocused, right? And if you don't have all four of them, right, exactly where they should be, then that will depend on whether you get a good crisp like this, or you get more of a, or do you get more like this? See these dots right here, these green ones, you know, where it's not focused in, you know, or they're even bunched even more together, you know what I mean? Because you see, when they say that, you know, you have one slit or whatever, you observe it and blah, 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 they're lying about all this stuff, okay? And we're going to prove it on the next whatever, right? But I want you to understand, right? If you had a baseball, right? Because this is the first lie, right? If you had a baseball and you threw it through these two slits, right? First of all, you couldn't do this because like I said, the de Broglie wavelength for a baseball or anything that has a bunch of mass, it's too small. You know what I mean? The more mass, the small. It's like a Planck length. You could never have these slits the size of the wavelength and put, you know, you couldn't do it because the mass is too big, right? The Broglie wavelength is too small. Okay. So even if we did put the slits together, right, and we made it this size, right, and you can see here's the size of a baseball. This would be your slit, right, and they'd be pretty close together, right, because remember the slit width wants to be smaller than the wavelength of the light, right? So here's a baseball, you know, pretend that was an electron. Here's the electron's wavelength, right? So the slit would be about that size, right? But I want you to think about it, right? They always say that you would have, if you put balls, shoot them through there, right? You'd get a clump here and a clump here that designate those two, you know, in sync with those two holes there, those two slits. And you'd have like a pattern like this, right? In a way, yeah, kind of. Yeah, okay, maybe. But I don't believe so. I don't think so, okay? Because if you have it like a gun doing it, the gun's just going to shoot it into one of the holes, okay? It's not going to go into both holes, okay? But if you think about it logically, if you went and got this, if we got this slits, right, and you got a baseball, an actual baseball, right, you can see it can barely get in there. It can barely get through the hole. Look at the size of these two things, right? Now, you walk away 40, 50 feet away, and I'll give you an unlimited amount of baseballs, okay? And I want you to throw them at these two slits that are this small compared to your baseball. And I want you to see, okay, if you get two clumps, like they say, that will sync up with the, you know, in line with these two slits. Boom, okay? Boom, okay? If I have a baseball and I have to throw it through a little tiny slit like this, a little hole like that, when the baseball can barely get through it, and I'm like 40 feet away and I got to throw it? No, first of all, most of them ain't even going to go into the hole, okay? Second of all, the ones that do get into the hole, look at this. You have like 50% probability of, you know, hitting one of the sides. And if I hit one of the sides, which I'm going to most likely do, it's not just going to go through there like swish. when I'm throwing 100 baseballs. No, that's not going to happen.